Hello everyone, my name is Kevin Saslawsky. I will be presenting this research, Branching Inventory, Democratized Fabrication of Available Stock. A bit about myself. I hail from Memphis, Tennessee in the United States. My undergraduate where this research was conducted was the University of Tennessee College of Architecture and Design. This research was part of a larger studio entitled Material Misbehavior under the visiting professors Katie McDonald and Kyle Schumann. All of the research you will see today was done in collaboration between my partner, Tyler Sanford, and myself. Branching inventory is a construction methodology demonstrated through a full-scale structural prototype that reduces the waste inherent milling lumber and celebrates natural variation by making complex form the efficient result of irregular material. The processing of wood into standardized components embeds waste and intensive energy consumption into timber construction. This work reimagines the utility of raw materials, using computational feedback to place natural form and dialogue with design intent, creating a dialogue between technology, material, and designer. During industrialization, wood construction became standardized through the milling of logs into dimensional lumber. This subtractive part reduction, repeated at forest, sawmill, and construction site, produces waste in form of offcuts as well as requires intensive energy use. Amid an escalating environmental crisis, dimension lumber faces new life cycle questions and overextended supply chains. The potential of computational imaging, 3D scanning, and fabricating non-standard timber have been both explored and demonstrated in built projects such as the AA Hook Park over the last several years. Most of this work relies on elaborate and cost-prohibitive 3D scanning and robotic fabrication. This paper describes a democratized take on such approaches, developing a novel construction methodology which reimagines the utility of raw logs using computational feedback to place natural form and dialogue design intent. Because material eccentricity informs design geometry, minimal part reduction must be performed, in turn decreasing construction energy and waste during harvesting, production, and on-site construction. The workflow is demonstrated through the construction of a full-scale structural prototype, a wall that is 10 meters in length and 3 meters in height. 25 meters in length and 3 meters in height. Invasive plant species, specifically the Bradford pear, which is invasive to the region in which the research was performed, are explored as a natural material stream for construction, attempting to incentivize the removal of such species and in turn, the remediation of the environment at the regional scale. The Bradford pear, which was popularized in yards and parking lots due to its natural ornament and fast growth, is prone to losing branches due to its weak, acutely angled forks and numerous limbs originating from the same point. The built prototype collects and makes use of these fallen branches. Branching inventory develops a hybrid analog/digital workflow which form many types of structures can be designed and built, which will vary in form according to material input and design intent. Seen on this page is the systems diagram which mediates designer, material, computation, and physical fabrication. The methodology is described in 5 main steps: collection and scanning, inventory and analysis, branch and surface sorting, programming joints, and physical assembly. To extract physical qualities from the irregular material which can inform a design, a reliable 3D scanning method was required. Several 3D scanning methods were tested, from consumer-grade smartphone apps to high-end industrial 3D scanning hardware and software. Ultimately, a user-friendly smartphone app, Clone, was selected. Clone is a photogrammetry scanning software that uses a printed calibration grid as the surface on which an object is scanned. The surface can be printed at any scale and isolates the digital model from all background material, meaning that no post-processing of the resulting digital mesh is required. An augmented dome is viewable around the object as it is scanned to direct the user to views and angles yet to be photographed. The use of a smartphone app democratizes the approach, replacing 3D scanners, which retail for tens of thousands of dollars, with software that costs a few $1,000s. This step of the process functions as the digital link between designer and material. First, the inventory is prepared for analysis with the goal of extracting specific understandings of the branch's inherent eccentricities, such that it can be used to the designer's advantage. The first operation performed on each 3D mesh was a simple contouring along the length of the branch that serves as a base for many other operations. Connecting the centroids of these curves result in a crude interpolated curve representing the center line of the branch, a spatial delineation that can be further refined by interpolating circles over each contoured section, in effect smoothing out branches with small protruding geometries. The generated center lines are linked to each individual branch and stored in the corresponding place within the inventory. The interpolated circles also serve to measure and calculate the average circumference of each branch. Using the new inventory of centerline curves, a set of curvature values are determined for each branch. A circle is interpolated from 3 points on the curve, representing the average curvature of the branch. Once all 60 branches are scanned and analyzed, they are numbered to match their physical identity, compiled into an organized grid on a single rhinoceros file. The data extracted, curvature and average radius, is crucial to understand and determine how the irregular material can be used accurately in predictably modeling and fabricating a structure. Having scanned and analyzed an inventory of branches, the next step is to correlate this material inventory with a designed form. The form was designed as a lofted surface between straight and undulating curve, resulting in a vertical wall-like structure that is serpentine at ground level and straight at its highest point. The designed mesh contains embedded information in each of its UV division curves that is similar to the information gathered in the branch inventory described previously. Each mesh edge has a particular associated curvature and has its own z height relative to the ground. These two values are evaluated and inventoried on the surface, as done with the branches. These new mesh values are compared to the branch values in a best fit system. First, the branches are sorted by average circumference and assigned to an appropriate horizontal section of the mesh, according to the z height. Next, beginning with the most extreme curvature values, branches are matched to the mesh edge with the most similar curvature value. After the branches are located across the surface, a joinery method is implemented to physically fabricate the structure, rather than relying on highly specific joints that must be scanned and machined into the ends of the branches. A joint system was developed that could connect the ends of the branches where they meet at the nodes of the surface. Multiple joint iterations were developed and tested, ranging in scale and complexity. Initially, joints anticipated the overlapping and capturing of branch ends, but this was deemed too visually clunky and complex. Instead, the final joint design required the branches to terminate just short of the intersection, slotting into a node made of two intersecting pieces of steel, a thin joint that does not distract visually from the legibility of the best fit system. To model and fabricate the joints, two planar surfaces were generated using the points of intersection between 4 branches. 2 triangles are created to hold these surfaces together for welding accurate angles and to reinforce the joint. Once the joint was adapted to the geometry of each node in the structure, They were cut from 14-gauge steel sheet and welded manually using the triangular alignment pieces. Joints at the edges of the assembly were generated with the same process with slight variation. The bottom joints connected to the ground were made with two metal plates folded and welded back to back, while the elbow joints on the ends and the top edges are simply bent to the correct angle to hold the edge pieces in place. Cutting the joints can be performed by either CNC water jet or a plasma cutter in a typical digital fabrication workflow, or in a more low-tech and democratized approach by using hand-printed paper templates and metal bandsaw or jigsaw. To attach the metal joints to the wood branches, 2.5-inch curve cuts were made into the ends of each branch to accept the joint. With the metal joint inserted, 2 holes were drilled through both the branch and the joint, through which bolts hold the assembly together and prevent rotation. The digital model was referenced visually to guide the correct orientation of the branches during the curve cutting and the assembly. Once fastened, the programmed geometry of the joints accurately positioned the branches in the correct orientation within the overall assembly, meaning that the assembly was easily completed in its correct upright orientation by a team of 2 individuals, without the use of scaffolding or any large-scale alignment templates. This research contributes to a body of work that advances applications of irregular, non-standard materials in the production of architectural structures. Ideas around material agency and minimizing waste in digital fabrication processes resonate with Bandsaw Bands, a project in which the natural forms of a tree flitch generated a 3-dimensional topographic surface, while ideas about scanning and building with logs offer alternative approaches to the process developed for making use of these tree forks in Tree Fork Trust by John and Foley. Furthermore, techniques aimed at minimizing part reduction build on the approach developed to make the use of concrete debris in Cyclopean Cannibalism by Clifford and McGee. Branching inventory contributes to this idea of scholarship by proposing and demonstrating the transformation of such methods to readily available democratized technologies. Not prohibitively expensive or cumbersome scanning or robotic fabrication equipment is necessary. The approach is globally transferable, usable by anyone with a smartphone, laptop, rhinoceros and grasshopper, and a few basic manual woodworking and metalworking tools. The project also advances an ecological narrative using material that is essentially landscape waste and would not otherwise be usable in architectural applications, specifically the use of material harvested from the invasive species whose existence is typically a nuisance, demonstrates the utilization of such material and incentivizes their removal and the subsequent remediation of the native ecosystems. Thank you for watching, and I hope you enjoy this research.